Hey folks, in a previous video we looked at Lewis structures and how to construct Lewis structures using the octet rule. In this video we're going to take a look at molecules that actually don't follow the octet rule. And there are many that don't. So how do we draw Lewis structures for those molecules, and what is the geometry of those molecules? That is what we're going to be looking at in this particular video. All right, so first we have the simple rule that in the octet rule that each atom in the molecule is surrounded by 8 electrons. One of the exceptions, of course, is hydrogen right off the bat, and we've already learned that because hydrogen has only 1 electron, and the only thing that hydrogen will do in a molecule is form a single bond with no non-bonding pairs of electrons. So once we have that understanding of the octet rule, then what we're going to do is we're going to first, of course, count the total number of valence electrons in the atoms within the molecule. And then we're going to take those electrons and we're going to distribute them in a way so that each molecule or each atom in the molecule is surrounded by 8. So we'll start by doing bonds, and I'm not going to go through it specifically here at this point because there's a previous video in which we've done that. So the first thing, of course, is that we're going to do is we're going to go ahead and look at the bonds in the molecule, which each contain 2 electrons. So we're going to start with those bonds, and then once we've established those bonds with 2 electrons each and single bonds, then what we do is we distribute the remaining electrons that we have to try to satisfy the octet rule for each atom. Then, of course, we have the situation if we don't have enough electrons with single bonds, then we add multiple bonds, etc. And again, I'm not going to go through that because that's in a previous video. We're going to focus here on situations where the octet rule is not followed. All right, so, and again, so here are some examples of molecules which do follow the octet rule. We'll note that in the case here that we've got, for example, nitrogen has 8 electrons, 3 involving 3 pairs of electrons in the bonds, and then a non-bonding pair of electrons. And again, we'll note here that hydrogen, of course, it corresponds to a situation where there is only 1 bond and nothing else. Here is, of course, carbon dioxide, which requires that we have double bonds in order to satisfy the octet rule with the electrons that we have in that particular molecule. So again, these are molecules which have satisfied the octet rule. All right, so what are some exceptions of the octet rule, and what are the situations where we do see exceptions? So an expanded valence set, which basically what we're talking about is a situation where we have more than 4 atoms bound to a particular atom. Obviously, if you've got more than 4 atoms bound to a particular atom, you've got a situation where they obviously are not going to satisfy the octet rule. You're going to have more than 8 electrons around the central atom. Of course, if you've got a situation where you've got an odd number of electrons, well, then in that situation, clearly you're not going to be able to satisfy the octet rule because you need an even number of electrons in order to have this octet rule satisfied in that situation. And then for small atoms like boron and beryllium, when they are central atoms, all right, in the molecule, because they have so few electrons to start, that those particular atoms as central atoms will not satisfy the octet rule. Boron trifluoride is an example. So let's take a look at that one. Here we have boron trifluoride. Now, how many electrons do we have in boron trifluoride? We count the valence electrons, and of course, boron has 3 valence electrons. Fluorine has 7 electrons, and since there are 3 fluorines, that's going to give us a total of 21 electrons for fluorine. So we have a total of 24 electrons here. All right, so let's go ahead and distribute them. And we can do that easily enough following the simple rules that we've learned in the past. First, single bonds to each of the fluorines around our central atom boron. And so that 3 bonds right there has already used up 6 electrons, of course, so that we have 18 electrons remaining. And if we take those 18 remaining electrons, and let's just go ahead and work on the fluorines, we can satisfy the octet rule for each of the fluorines by taking those electrons and distributing 6 non-bonding electrons around each of the fluorine atoms, and that's a total of 24. Now, normally we would say, okay, boron clearly doesn't satisfy the octet rule here because it only has 6 electrons. Under normal circumstances, we'd go ahead and add a double bond in a situation to actually satisfy the octet rule. But it turns out that because boron is such a small atom, that we're only going to leave it at this, meaning that the boron does not satisfy the octet rule. We're not going to add a double bond to it. And actually, if we use formal charges here, we can see that this is going to be the most stable structure. And again, you might want to review how to generate formal charges for these, but we're going to note that each of the atoms in this molecule has a formal charge of 0. So that's actually, what we're kind of shooting for. Generally speaking, that if the formal charges are 0, that is the most stable configuration of electrons in the molecule. And so there's boron trifluoride, an exception to the octet rule. What about others? As mentioned, clearly if you have more than 4 atoms around the central molecule, like in this case we've got sulfur hexafluoride and phosphorus pentachloride, both of these particular molecules have more than 4 atoms around the central, and clearly in a situation like that, there's no way you can satisfy the octet rule. Because according to the octet rule, that the maximum number of atoms that could be surrounding central atom would be 4. You'd have 4 bonds, that's 8 electrons, and so clearly these don't work, all right? We can look at some specifics of the bonding and the orbitals involved in this. We're going to see that this happens typically when we have a D shell in row 3 or higher, where we got 3D electrons, for example, 3D electron orbitals that could actually be involved in the bonding for this situation. And under those circumstances, when we have 3D orbitals, then we've got 3D or 4D. We've got a situation where we could exceed the magic number of 8 electrons. So let's take a look at a specific example of sulfur hexafluoride. Again, go to the periodic table. We're going to note that sulfur has 6 electrons. Each of the fluorines has 7. There are 6 fluorines, so we're going to have a total of 42 electrons for that, and that means we're going to have a total of 48 electrons to distribute. So we can go ahead here and we'll just add our 6 fluorines, right, with the 6 bonds. And what does that mean? Well, we got 6 fluorines and we got 6 bonds, so we've used up 12 of our 48. Now we have 36 electrons remaining after we've used up those. And so let's go ahead now. We can purely, just simple arithmetic, we can see that if we satisfy the octet rule for each of the fluorines by adding 6 additional electrons to each of the fluorines, then that's going to use up all 36 remaining electrons. And so this is just going to be the simple structure here. That we're going to get for sulfur hexafluoride. We've used up all 48 electrons. Clearly the sulfur does not satisfy the octet rule. The fluorines do, but the sulfur does not. And so this is a situation we have, the expanded valence here, where we've got more electrons to distribute than would be necessary to satisfy the octet rule. So we've got too many electrons here in this case because we've got 6 fluorine atoms around that central atom. So that's, again, an exception to the octet rule. All right. Some other exceptions, obviously, you've got an odd number of electrons. We've already mentioned this, that you're going to have a situation where you're going to have an odd number, an extra electron, and this is what we talk about free radicals. All right. When we look at free radicals, we're talking about unpaired electrons being present. These are generally very unstable situations. All right. In molecules, being a free radical means it's really reactive because electrons want to be paired. And so in that situation, again, we're not going to satisfy the octet rule because we have an odd number of electrons. So in this situation, we've got some molecules of nitrogen, for example, which because nitrogen itself has an odd number of valence electrons, we've got 5 electrons on nitrogen. And when we combine that with other atoms like oxygen, like these nitrogen oxide molecules depicted here, then you are going to have an odd number of electrons. And so then you're going to have unpaired electrons. Nitrogen monoxide, nitrogen dioxide indicated here in this tend to be produced in automobile engines, for example, when you get combustion reactions. So you are combusting gasoline with air, and there's nitrogen in the air. So the nitrogen will react with the oxygen in that combustible high pressure situation that will generate these nitrogen oxides. And that's one of the purposes actually of catalytic converters that, and this is something that we may talk about later, but catalytic converters actually are designed to help remove these nitrogen oxides before being emitted as exhaust in these situations, because it is that these nitrogen oxides are pollutants and they are toxic. So the catalytic converter helps to remove those. They lead to photochemical smog and actually the production of ozone in the lower atmosphere. Okay, so let's take a look at nitrogen dioxide here, draw the Lewis structure just to demonstrate how we can't possibly, although it should be intuitive, we can't possibly satisfy the octet rule with an odd number. So we've got 5 electrons here for our nitrogen, valence electrons, and 2 oxygens, each with 6, so that's a total of 12 electrons for the oxygen, and therefore 17 electrons altogether. Obviously, odd number, again, there's no way, right? There's just no way. All right, so we'll start by drawing it. Here's our basic Lewis structure with just the bonds, starting with the bonds. And so we've used up 4 of our 17 electrons. We've got 13 remaining. Now we can choose to go ahead and satisfy the octet rule for the nitrogen. Doesn't really matter what we start with, but we'll do that. So we're adding 2 non-bonding pairs. Now, nitrogen has a total of 8. We have 9 electrons remaining. So we'll go ahead and do oxygen. All right, so now that oxygen satisfies the octet rule. But now we only have 3 left. And so clearly there's just no way this is going to work. All right, we can take a look here at what we might do in this situation. We can start adding multiple bonds. We can start looking at formal charges. So let's just go ahead and look at some examples of how we might do that. So let's just go ahead and form a double bond here by taking 2 of the electrons on our nitrogen. All right, and we're going to just leave this one in place. All right, so we take a look at that, and let's take a look at formal charges to see what we've got. Remembering the basic rules here that we're just looking at the number of valence electrons. So oxygen has 6 valence electrons. If we look at the number of electrons using our formal charge rule here in this particular oxygen, we'll note that we've got 3 non-bonding pairs, and of course in the formal charge rules, we take half of the electrons in the bonds, so there are a total of 5 electrons there associated with the oxygen, which is 1 less than the 6, and so the formal charge on that oxygen is a plus. All right. We'll do the same thing on the nitrogen. Remember, the nitrogen has 5 valence electrons. All right. And so if we go ahead and count the number of electrons here in the nitrogen atom, there's 2. And then we've got 3 bonds. So we've got 3. We've got a total of 5 electrons there in that nitrogen. And that means that we're happy here because nitrogen has a formal charge of 0, and then this one is going to have a formal charge of -1. Remember, when you add up the formal charges, they should add up to the charge of the molecule, which is 0. In any event, what we've drawn here is our situation for an exception to the octet rule because we have an odd number of electrons, and again, there's no way that we're going to get it in this situation. So we can draw some other resonance structures, obviously, for this molecule. We could switch sides with a double bond. I'm not going to bother to go through that. I just, again, want to demonstrate here that we have not and cannot satisfy the octet rule for this particular molecule. All right, so we're going to move on to some other examples of exceptions to the octet rule. And in this case, we're looking at a situation where we can construct a Lewis structure which actually adheres to the octet rule, but if we start looking at things like formal charges, we're going to find that it doesn't really make sense. Again, this is going to be the case with this expanded valence where we've got d shell orbitals that are available that can allow us to exceed the octet rule. And so sulfur being in row 3 actually is one of those atoms that has these empty d shell orbitals that can be used for this. So here we've got sulfate. If we do a normal Lewis structure, again, we can count up the number of electrons. Our sulfur has 6 electrons. It's below oxygen. Oxygen also has 6 electrons. So we've got 6 plus 24, that's 30. And then we've got a charge of -2, so that's 32 electrons. We can go through this process with 4 oxygen atoms attached, and we can add non-bonding pairs of electrons. So every atom here, the oxygens all satisfy the octet rule. The sulfur satisfies the octet rule. We're good. This is great. The problem is if we start looking at formal charges. And if we start looking at formal charges here, what we're going to note is that the oxygens, which have 6 valence electrons, each have a formal charge of -1. So each of our oxygens has a formal charge of -1. The sulfur, because it has 6 also, but only has 4 bonds, is going to have a formal charge of +2. Now those formal charges, since every atom has a non-zero formal charge, and particularly because sulfur is +2, is not actually preferred. So if we draw a better structure for this, and this is one of several resonance structures we can draw, let's put double bonds, and we add 2 double bonds here to the oxygens. And now we're going to note that these 2 oxygens now have 6 electrons, so the formal charge on these 2 oxygens is now 0. The formal charge on these 2 oxygens, the same as over here, is -1. So we've got 2 oxygens now have 0 and 2 oxygens that are -1. What about the sulfur? Well, the sulfur now has 6 bonds associated with it. So because it has 6 valence electrons and 6 bonds, it now has a formal charge of 0. So we've gone from a situation here where every atom has a non-zero formal charge. In this situation here, each of the oxygens has a formal charge of -1, and the sulfur has a formal charge of +2, to a situation where the sulfur is 0, 2 of the oxygens have formal charges of 0, and then 2 of the oxygens have formal charges of -1. That's much better. And so this would be the preferred resonance structure for the sulfate. Now, obviously, we could draw double bonds to these oxygens. We could switch things around. So we can draw additional resonance structures for this, which has an impact on how the molecule actually, in the real world, its actual geometry and the actual bond lengths for the molecule in the real world would all be the same. But measurements certainly do indicate, rather than single bonds, that we've got a situation where the bonds, sulfur-oxygen bonds, are actually shorter than what we'd expect for a single bond, which confirms that this resonance structure and its compadres are the preferred structures. What about geometry? So VSEPR theory, remember, tells us how we should expect to arrange electrons to minimize electron repulsion. In other words, getting the electrons as far apart from each other as possible to minimize electron repulsion, and how we do that. So we've already looked at these basic structures. Just a quick review here. Looked at these in previous videos. 2 electron groups, a bond angle of 180 degrees would give us a linear. All right. If we've got 3 groups, and BF3 would fit into this because BF3 has 3 groups of electrons around the central atom. So that's going to be the trigonal planar configuration. Tetrahedral configuration with 4 groups of electrons around the central atom. And so let's look at the situation. If we've got
PF5,
we've got 5 atoms around the central. So we're going to have an arrangement like this, and this is called a trigonal bipyramid, all right, with this structure. Sulfur tetrafluoride has a non-bonding pair of electrons. Again, you can confirm this if you draw the Lewis structure. And in that case, we have a situation which is interesting here and is different from every other geometry that we're talking about, where we've got 2 different bond angles. The bond angle between, this is called, these atoms here that are up and down are called the axial positions, and the positions here around the center are the equatorial positions. And the bond angle between the axial and the equatorial is 90 degrees. The bond angle between the equatorial is 120 degrees. So these are non-equivalent positions. Unlike the tetrahedral structure, unlike the trigonal planar structure, unlike the octahedral structure, which we're going to talk about next, these are non-equivalent positions. So if we have a non-bonding pair of electrons, one of the questions is, where do we put it? All right. Is it in an axial position or an equatorial position? It's going to go in a position that minimizes electron repulsion. All right. That's the key. It's going to minimize electron repulsion. So if it minimizes electron repulsion, turns out putting the non-bonding pair of electrons in the equatorial position is better than the axial position. It minimizes it more. In the axial position, that non-bonding electron pair would have 90-degree angles to 3 atoms, as opposed to the equatorial position where it has a 90-degree angle to 2 atoms, but then a 120-degree angle to the others. And so this is the configuration which has lower electron repulsion. So with that one non-bonding pair of electrons, what we're going to see is this particular structure, which is called a seesaw structure, if you can imagine it looking like a seesaw. What about 2 non-bonding pairs of electrons? Again, any non-bonding pairs of electrons go into the equatorial position, all right? So this is just a T shape. You can see it looks like a T for bromine trifluoride with 2 non-bonding pairs of electrons. And then xenon difluoride, all the non-bonding pairs are going to be in the equatorial positions. And so this is just going to be linear. And again, when we talk about the naming of the geometry, we're naming the geometry based on the positions of the atoms, not on the positions of the non-bonding pairs of electrons. So even though this is structure here for xenon difluoride is based on trigonal bipyramid, the positions of the non-bonding pairs are such that if we just look at the positions of the atoms, it's a linear molecule. All right, so those that's a situation where you have 5 groups of electrons around the central atom. And then the octahedral structure is when we have 6 groups. We've already looked at sulfur hexafluoride. In that situation, it's just, we've got this is called an octahedral structure. if we have non-bonding pairs of electrons, it doesn't matter where they go because all the positions are equivalent. Now it's drawn here, so it's in the lower position for this non-bonding pair of electrons, but you could put it anywhere and it really is the same thing. You can rotate the molecule around. It's just going to look the same. All the positions are equivalent here. So one non-bonding pair, it's going to go in one of those positions. If I've got two non-bonding pairs, we're going to put them on opposite sides because that's going to minimize electron repulsion. So rather than having a non-bonding pair here and here, for example, where the angle between the non-bonding pairs is 90 degrees, we're going to put them opposite each other. And so this is called a square planar position because it's just going to look like all of the atoms are in a plane and it forms a little square. All right. And so that's our octahedral geometry then that's based on 6 electron groups. Again, these are situations where we're not adhering to the octet rule. So that's basically the summary of a situation where we're not adhering to the octet rule. So that's basically, at this point, we've looked at examples of molecules that don't adhere to the octet rule, and we've looked at the corresponding geometries for those molecules that don't adhere to the octet rule. I hope this is clear. As usual, if you have any questions, let me know.